Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. So, uh, my name is Saida Razali. I'm will teaching you mathematics in networking. So the old course code is WRES 2109. I think this one intended for 2016 and below, and WIC3001 is beyond 2016 students. So I just use both codes because I don't know, that's required by the system anyway. So this is my email. Um, so this is my email. My my room is B-2-14 block B. So I mean this is a slide that I prepared for physical classes, but since anything, if you want to email me, I think if you want, it's good to have a WhatsApp group because sometimes it's much more faster there. So I will just try to, I don't know, appoint one class rep from your batch, and then try to create a WhatsApp group. So this is my phone number. So just add me and try to create a group for this mathematics in networking, since we will go fully online the whole semester. Okay, so this is the course content. So the first part of this is the discrete probability, and then the second one is the graph theory. Graph theory has a lot of I think the graph theory I cover the most topic that I cover in this course. And then you have a queuing theory, sorry, and then you have a network calculus. So these four big topics for mathematics in networking. Okay, sorry. So these are textbooks, Discrete Mathematics and its application by Kenneth S. Rosen, but this one is more on the graph theory. So like network probability, you can use discrete probability, you can use any other statistical books, and queuing and network calculus is mostly from engineering mathematical books, from electrical engineering. So this is the grading criteria. So you have a continuous assessment, which includes tutorials, quizzes, assignments, and midterm exam. So this is all just that quiz. I'm not sure how to do the quiz and tutorials. Maybe I just convert tutorial and quizzes into like assignment. Um, Maybe assignment. I mean, all these tutorial quiz assignments will just bunch into one. I mean, a couple of assignments, and of course, a midterm exam, 20%. And of course, we have a final exam, 50%. So all the notes will be available in Spectrum, your Spectrum, as long as you register with this course. So lecture tutorial within this semester will be fully online. So, okay, not tutorial, but it's more like assignment in soft copy. Last time quiz in hard copy, but no, quiz also will be in soft copies. So this is just the rules. That UM quality objective states that student must attain 80% attendance to eligible for sorry to sit for the final examination. I think mostly on the QR code or the Google Sheet attendance, but mostly on the QR code. I'm not really keen on this. I mean, this is the online. I will do mostly if I have a live lecture or recording lecture, which is you can attend, you can hear, or you can like study anywhere. I mean anywhere and whatever time that you know feel comfortable. I know some of you doesn't have a really good connectivity at your home, but hopefully you can follow this class. So because of the this CMO, control movement order, I think some of you think it will be unlucky, but for me, most of the lecture during this CMO is not. I mean, their empathy. You know what is empathy? It's very high. So most probably student will, I don't know, they will give chance to students, and then so you should score the subjects. I mean, I consider because you have to study at your home. Some of you like home, you have a big family, your environment to study is not there, and everything. So that's why I said empathy. Most of the lecturers here, I mean, I think all over UM have quite a big empathy for these online courses. So just do your best and try to follow my lectures. If anything, you can ask me. I will open a forum, or you just can ask me through WhatsApp group if you create groups. Okay, we're gonna start our lectures now. So I'm gonna go fast in the discrete probability. And first, I have to apologize since this semester I just want to this semester, first it's a fully online, and I also have an industrial project with Petronas. So expect class cancellation. The problem with the industry is, I already have this. My project is already approved by VCs and stuff. Actually, I'm planning to do industrial leave for 1 year, but of course, um, we don't have that many lecturers, and some of the lecturers student doesn't want to take their subject whatsoever. I think I don't know. Most of you knows about this, and for some reasons, my subjects. I also have to open another subject, parallel programming, which is I don't really keen to to open that because this the first time I teach this subject. Not the first time. This is the first time any lecturers take these subjects to teach. It's the last semester. So within because I have some industrial project has been ongoing since last semester, so I don't have time to improve the subjects. But they asked me to open anyway, so I already told them. As again with this class also expect class cancellation and stuff, but I will be very flexible. I mean, you can. If I set your assignments to submit within certain period of time, just try please to complete the assignments. Okay. So and because of this today today I have to attend a safety briefing from Petronas. Safety briefing, so I have to pre-recorded lecture for Monday, Tuesday, for 19/10/2020. So just expect, if you done industrial project, you cannot just, if there is a problem, you cannot just like expect Petronas to, I'm sorry, I cannot attend to your problems because I have class teach whatsoever. This is not acceptable for industrial. But since I hope that you are flexible, because I'm flexible, can give lecture record. But worst case, I just, just post I think all the lectures I already put in the spectrum. Worst cases, I just ask you to, you know, just read the lecture slides that I already posted in the spectrum. So the discrete probability. So we're gonna do it very fast. So roughly speaking, it's a set of collection of objects that satisfy certain property but in set theory, the word set and element are intentionally left as undefined. So there's also an undefined relation with this, reverse E or called element. membership. So if S is a set and A is an element of S, then we write A is an element of S, and we can say that A belongs to S. So you have here like, oh, sorry, you have here like this one, big one, this is the S, and this is A. So you write A element of S, something like that. And you have close curly brackets, open and close notation. So like if set M has only a finite number of elements, say 3, 7, and 11, 7 and 11, then we can write M, set of M is 3, 7, and 11. So you have M here. This is set M, you have number of 3, 7, and 11. The order in which they appear is unimportant. It can be 7, 3, 11, 11, 3, 7, and so on. So a set can also be specified by defining property. For instance, set is x element of R, which is in the range of -2, less than x, less than 5. So if you have this, you have actually S is a, you can write this one is a -1, 0, 1, 2, 3, and 4. Sorry. So this is basically S. This is almost the way to define an infinite set. So this is like the I'm not saying, this is what the academics or mathematician likes you to express this one. But this is the real or absolute answer for that. I'm okay. We're not really. This is just a basic. This is just just to recall that your basic probability that you learn during your your foundation or school, or maybe first year. I'm not sure. So the basic definitions, some basics axioms or definition of terms. Axiom of pairing: for any A and B, there exists a set AB that contains exactly A and B. So this is pretty much, this is pretty much self-explainable. So axiom of extension: for any two sets A and B, or this is the reverse A, or meaning is for all. A equal to B is actually for all X, which X is element of A, and of course the X element of B. So two sets A and B. So just that this is A equal to B, and this is the with not with respect to, just like some equal sign. If all element is actually all element of X, where X is element of A, and X is also an element of B for all X. In other words, two sets are equal if and only if they have the same elements. For example, 1, 2, 3, 3, 1, 2, 1, 2, 3, 2. Okay, you can say this is a set A, this is set B, and this is a set C. So you can say S is a subset of T, means that every element of S is also an element of T. Sorry for that. Let me just, okay. So this like S subset of T. So you can say like all this T you have like 1, 2, and 3. So A is a subset of T, B subset of T, and C is a subset of T. So conceptually, sets may be infinite, not finite, without n, unending. Symbols for some special sets may be infinite or it can be finite. So just don't worry about that. Symbols for some special infinite set is n is equal to 0, 1, 2, the natural numbers. Natural numbers are non-negative numbers. Z is equal to no minus infinity until positive infinity, the integers. And R is the real numbers. So real numbers, which is if we try to divide that, it will be no end. There's like pi and something else. So infinite sets come in different sizes. So this is just a notation of zero or null, the empty set. It's a unique set that contains no element whatsoever. So the union operator or the OR operator. For sets A, B, the union A union B is the set containing all elements that are either in A or V in B, of course, in both. So, example, you have A, B, C, and 2, 3. Okay, A, B, C, 2, 3. And you have 2, 3, 5, and 3, 5, 7. 2, 3, 5, 3, 5, 7. You have 2, 3, 5, and 7. So you can say this is the element A, B, C, 2, 3. So this is A, B. And this is like, okay, you have here, there is 1, 3, and 3. Sorry, erase that. So you have here two sets. You have 3 here, and then you have here is 3 and 5, I guess. Sorry for that. And you have here 7, and you have here 2. So 2, 3, 5, 7, 3 and 5 is intersection. So this is a union. You include all this in the set. For sets A and B, for sets A, B, their intersection A, intersection B. Okay, this is union, which is more to OR. Okay, you have here OR. And then for sets A and B intersection, all elements that are simultaneous in A and. So you have here and. So intersection is here and OR is union. So example A, B, C, and 2 and 3. So there are no like same elements. So it's a null. So 2, 4, 6, and 3, 4, 5, you only have 1 here and 1 here. So you have here 4 n. So two sets A and B are called disjoint. Unjoint if the intersection is empty. A intersect B is null. So example, the set of even integers is disjoint with the set of odd integers. So you can never have the same even and odd integers or numbers. So set complements. The universe of this course can itself be considered a set. Call it U. So U is a universe of this course, or you can just use universal. Okay, and then we want to say about complement. Not complement is more on not. So remember, this one is OR, this one intersection is AND, and if you have a complement, it's a not. Okay, you have a complement of I, something like that. Complement of A is written as A complement is the complement of A with respect to universal. It is U minus A. Okay, universal minus A is complement of A. So let's say if U is what N is, N is the natural numbers. If n is a natural number, so complement of 3 and 5 is 0, 1, 2. Each number positive number, excluding 3 and 5. In problems, you will recognize that you are working with union if you see the word OR. Okay. This is and then intersection if you see the word and. So this is a symbol, and complement if you see the word not. So you have A complement. So this is the bar above that. This is all you have learned. So this is identity. A union null is equal to A intersection with U. Domination A union U is U. A union U is U. A intersection null is null. Idempotent is like whatever you do, how many multiple process you have done, it yield the same results, like multiply with 0. Regardless how many you multiply a number with 0, you will get the same results. So A union A is equal to A and equal to A intersection A. This is idempotent. Double complement or commutative, A union B is equal to B union A intersection B is B intersection A, pretty much self-explainable. And associative features A union with B union C is equal to A union B union C. A intersection B, A intersection with B intersection C is equal to A intersection B intersection with C. So this is all, easy for you. So unbiased dice. This is some American or British, never mind. The sample space S is a set of all possible outcomes. So dice have six. So deck of card has total 52 cards. Okay, from ace to king. If you play cards, okay, from ace to king. So tossing a coin outcomes is you have a coin whether it's head or tail. Usually use outcome. Coins to if you're playing football, which side will start to kick first, or something like that. And rolling a dice outcome is 1, 2, 3, 4, 5, 6 numbers. And then rolling two balanced dice, you have 36 outcome because the first dice you have 6 outcomes, and the second dice you have another 6 outcome. You just like multiply 6 times 6. Okay, 36 outcomes. So any subset of sample space. Let's say you have event 1. The set in event 1 is number 3. Sets in event 2 is 2 and 5. Okay, experiment procedure that yields event. So you have E1 and E2. The event E is any subset of sample space S. So S is the big one, sample space, and E is the subset. Okay, E is a event that happened in S. The event E is said to have occurred if after the outcome has been observed and the outcome lies in E. So that is an event E. And you have an event E in S. So event E is said to occur happens if after the outcome has been observed and the outcome lies in within the event E. So rolling a dice, outcome is 6. Let's say E event, the event that even number is rolled, so 2, 4, and 6. So you have 3 over 6, 1 over 2. Okay, so you have here 3 over 6 or 1 over 2, even number. Same with the odd number as well. Probability measures the degree of uncertainty about the potential outcome of a process. So probability of E is size samples. So you know this one. So the probability cannot be more than 1. Okay. So probability that dice bring 3, so 1 over 6, pretty much. 2 or 5, 2 over 6. You have 2 unbiased dice, and then you have events. What is the probability that 2 dice bring 1, 1, so 1 over 36, sort of. What is the probability that 2 dice bring same numbers? So you have 1, 1, 2, 2, 2, 3, 4, 4. So you have 1, 2, 3, 4, 5, 6. And the sample size is 36. So we have 6 over 36. Okay. So S, you have 36. F 36 and E is 6. So 6 over 36 or 1 over 6, something like that. So enumeration methods. The addition rule. First one you learn is the addition rule. If there are n1 ways to do task 1 and n2 ways to do task 2, and if this task can be done at the same time, let's say you can watch your favorite Netflix program. I don't know what students nowadays. I don't know whether you watch like Breaking Bad, and then you can do you can watch Breaking Bad. That's my favorite show, by the way. And then you can also eat pizza at the same time. So, okay, you cannot do if you want to watch Breaking Bad at the same time uh, you want to watch Breaking Bad, but at the same time you want to go outside cycling or something, not indoor cycling, outside cycling, you cannot do that. Okay. You then there are n1 plus n2 ways to do one of these two tasks if the task can be done at the same time. So there are n1 plus n2 ways to do one of the tasks. We must make one choice or a second choice. So the keyword is or. You can just plus or add. Okay. Sample question. There are 18 maths majors and 32 computer science majors. How many ways there are to pick one math major or one computer science major? So it's one math major or one computer science major. So according to the addition rule, you just add n1 plus n2. In this case, n1 is 18, n2 is 32, and you have 15. Okay, this one is n1 and this one is n2. So multiplication principle, there are n1 ways to do task 1 and n2 ways to do task 2. Then there are n1 times n2 ways to do both tasks in sequence. Cannot occur at the same time. This applies when doing the procedure is made up of separate tasks. We must make one choice and a second choice. So there are 18 math major and 325 computer science majors. Both tasks in sequence. Not necessarily can be, can occur at the same time or can occur not at the same time, something else. But this is the intersection multiplication principle, and it's more associated with the AND logic. So there are 18 math majors and 325 computer science majors. So how many ways there are there to pick one math majors and one CS majors? So you just multiply 18 times 32 and 576. This is n1 and this is n2. So permutations. Okay, permutation is set of objects and arrangement of those objects in definite order without repetitions. So number of permutations of set with these three elements is n factorial is equal to n times n minus 1 times m, so is equal to npr permutations. So number of permutations of the set 1 to 3 is 3 factorial. They are 1 2 3 1 3 2 2 1 3 2 3 1 3 1 2 3 2 1. So you can see this, the order is important. 1 2 3 basically is the same one, but you have order 1 2 3 1 3 2. The order is important. The number of two permutation of set 1 2 3 is 6. There are 1 2. So let's say you want to set the number of two permutation of the set 1 2 and 3 is, so you want to set from this 3 you want to set, you want to two numbers only, and the order is important. 1 and 2 and 2 and 1 is different, so you use npr. So you remember permutations, order, in order is important. Okay, so combinations and CR, which basically the opposite of permutation, which is order is not important. Okay, and you have this one 3 subset size 2, so you have 1 2 1 3. So 1 2 or 2 1 doesn't matter, 1 3 or 3 1 doesn't matter, same 2 3 or 3 2 doesn't matter. So the keyword is order matters, use permutations. If order does not matters, use combination. So this one is NPR and this one is NCR. Just to recall back. So counting methods. Example: deck has 52 cards, 13 kind of cards. Okay, each kind has 4 suits: hearts, diamond, clubs, and spades. You draw one card from a deck of cards. What the probability that you draw a queen? How many queen you have? 4. 4 over 52. Okay, so what's 0.769. So if you I think you all, if you know, like cards, if you have played cards before, I don't know, blackjack or something. Blackjack or so maybe solitaire. I mean, solitaire is like Windows things. Okay, we continue. How many ways can a team of four people be chosen from group of nine if the order in which the people are chosen matters? So if like you want to, one many ways team of four people can be chosen from nine group of nine. So you want four, and order is matter. One who seat number one, who have seat chair number one, chair number two, three, and four is important. Okay, so you have nine P4. So in order which people are chosen does not matters. So it can be anyway. So 9 4 is 1 2 and 6. Let's say you have here you mean A B C D E 1 2 3 4 5 C D E sorry F G 1 2 3 4 5 6 7 8 9. So you have four people. You can use A B C D D C BA, even though this same but the order is important. This one A first and this one D first. So that's why you have C 2024. But this one, if you A B C D, it's just the same with D B C A or D A B C. So this is considered one and CR. Just to recall, I think you all know that. And axioms of probability. The probability function P is defined on subsets of the sample space S to satisfy the following axioms. Non-negative probability. So pretty much you don't have a negative probability. Mutually exclusive events. Events are independent of each other. Cannot occur at the same time. So you have a P probability of E1 event 1 union with event 2 is equal to P event 1 plus P2, provided P E1 into a mutually exclusive. E1, E2 is empty, the universal set. So if like mutually exclusive, E1 and E2 is a difference. So E1 and this one is E2, doesn't intersect with each other. Okay, no intersection. And the universal set PS is equal to 1. So probability complementary events. So you have a P probability of complement E is one minus probability of E. So this is just a proof, pretty much straightforward. Okay, go for the example. What is the probability that the binary string of 3 bits contain at least 1 0? So you have here 3 bits, so 2 to the power of 3. Sample size is 8. So what is that? Binary string of 3 bits contain at least 1 0. So if you would take 1 0, if 1 1 0, 1 0 1, at least 1 0, so 2 and more. Okay, you have 1, 2, 3, 4, 5, 6, 7. And then E 1 1 1. Okay. It's either you can 1 minus 1 minus 2 over 3, 1 minus 1 over 2 to the power of 3, or you just can say like at least 1 0 is 7 to the power 2 to the power of 7 over 8, something like that. Okay, property of an event, the empty set. So P theta is equal to 0. P null is equal, probability of null is equal when null is the empty set. So you have here PS union theta is equal to PS plus P null. So this is pretty much forward as well. And this is the addition law of probability. If event 1 and event 2 are subsets of S, then P event 1 union with event 2 is equal to PE1 plus PE2 minus PE1 intersection with E2. So proof you have here. Here you can do the proof yourself. I think this is also straightforward. You just replace, and then you have this, the equal number one, and then you replace this in. Okay, you just replace this one, equation number one to equation number two. This is proof. So the addition law of probability, the probability that a student will pass mathematics is 0.8, and that she will pass physics 0.65, that she will pass both courses is 0.6. So find the probability that she will pass at least one of the two courses. Okay, you know that this the addition law of probability saying that uh, addition law of probability say you have a p maths physics is equal to p maths plus probability of physics minus p maths intersection with physics. Okay, you know pm is 0.8, p physics is 0.8, p physics is 0.65 minus pmp is 0.6. She will pass both 0.6, so you yield a 0.85. Straightforward. So what is the probability that a binary string of 8 bits start with 0 or ends with 11? Strings that start with 0 is, okay, this one, and you have a 0, and you have 8 bits, and then you have 1, 2, 3, 4, 5, 6, 7. So this is 2 to the power 7 ways you can, arrange it, 0 or 1. So E1 is 2 to the power 7, string that ends with 11. So 2 to the power of 6, not 11, 1, 1. So 1, 1, so you have 2 to the power of 6, 1, 2, 3, 4, 5, 6. Doesn't matter, all these 6, what we call that, 6 binary, the first 6 binary, okay? And you just put the equation here, and then start with 0 and ends with 11. So you have a 2 to the power of 5, 0 and 1. So you in the middle, you have 1, 2, 3, 4, 5. 0 and end with 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 6, 7, 8, 9. Oh, this one is actually sorry. Okay, just error. 1, 2, 3, 4, 5. 3, 4, 5. Okay, this one you don't have. So just remember that. So 2 to the power of 5. So just put the formula and you have that 5 over 8. What is the probability that a binary string of 8 bits start with 0 or ends with 11? P even 0, even 1, ends, or even 2. So E1 is a string start with 0, E2 is string that end with 11. So suppose bag contains 6 balls, 3 red. Okay, this want to learn like Bayes theorem. Suppose a bag contains 6 balls, 3 red and 3 white. 2 balls are chosen without replacement at random, one after the other. Consider the two events A and B. A is event first ball chosen is red. B is event second ball chosen. So if PA is easy, 3 over 6. However, PB is different because let's say if it depends on the event A, probability of A, event A. So the probability of B occurring is conditional. This is what like a conditional probability. In order, event B is dependent on event A. Conditional probability. Okay. So conditional probability or written as PA given B. and read as the property of A given B, and is calculated as PA even given B is PA and B intersection over PB, or the other way around is PBA is equal to PA and B equal PA. Alright. Yeah. So this is a conditional probability. So E given F already, what is the probability of E given that F occur? So this is what the meaning of P given F. Okay. So this example, in a given country, 90% of household own TV. So you have here PTV. PTV is 0.9 of household own a TV, and 44% own both TV and VCR. Okay, VCR is prehistoric. I don't know whether you guys have seen the DVD player, I guess. So VCR is like tape, an analog tape, using just a tape. Okay, so PTV and VCR is 0.54. So I want to say that the household with TV also owns a VCR. So you given TV and VCR, PVCR when TV. So you use this formula and you get 0.6. In that example, what is the probability that a family of two children has two boys given that one child is a boy? So you have two child. So you have boy girls. So this is the way you BB, BG, GB, and GG. So you have 4. The sample space is 4. One child is a boy. At least one child is a boy. BB, BG, or GB. Okay. Two child boys, one child. Now you have EBB. Both children are boys. So you just use the formula and you have a 1 over 3. So PEF is a PBB. PE and F has two boys given that one child is a boy. So PBB is 1 and sample size is 4. And then PBB, BG, and PB is 3 over 4. Okay, PF. So F is here, 3 over 4. So independence. One of the objectives of calculating conditional probability is to determine whether two events are related. In particular, we would like to know whether they are independent. So, independence. We want to know like two events A and B are independent, meaning that PA doesn't depend on B and vice versa. It's just like that. What do you call that? Let's say if you want to play football, if it's raining, you don't play football. So this is dependent on each other. But like even B, you want to go to eat, it's raining, so it doesn't matter whether it's raining or not, you will go to it. So this is independent, sort of. So independent events, say that E1 and E2, event 1, event 2 are independent if P event 1 intersection with E2 is equal to PE1 times PE2. Okay, so you have a P, and like PE1 E2 is equal to PE1, or PE2 E1 is equal to P1. It doesn't matter. So you have here PE2 E1 also is equal to PE1. Sorry, PE2. Alright. So 4-bit uniformly random strings. Event 1 is a string began with 1, and event 2 string contains odd number of 1. So you have E1 4. So you have a sample size. How many? 2 to the power of 4 is 16. So you have a E1, a string begin with 1. You have 1, 2, 3, 4, 5, 6, 7, 8. And then E2 you have string contains odd number of 1. 1 and 3. 1 and 3. So E1, E2 is 100, 1011, 1101, 1110. Okay. Sorry. Okay. So E1 is equal to E2. Event 1 equal to E2 is 8. So if E1, E2 is 4. So if you use the formula P1 is equal to PE2, use the formula it is independent. So you have PE1 and PE2. So E1 and E2 are independent of each other. Okay. E1 can occur without E2, and E2 also can occur without E1. And then probability is the limit of observed frequency as number of observation goes to infinity. It's purely descriptive. Let's say okay, now probability is 70% of November days in Zurich are rainy. So this is the way that you collect the data over the years. You can confidently say that 70% of November days in Zurich are rainy. Okay, and you have another one is Bayesian. Probability is a degree of confidence that one attached to an uncertain event. There is a 30% chance of rain tomorrow. So this is highly speculative. Okay. Okay, this is a descriptive. Descriptive. You collect the data over the years and you can confidently say 70% of November days in Zurich are rainy. So this one, number 2 is we call that this is descriptive, this is speculative. Oh, sorry. You can say this is speculative. Of course, with the Bayesian, I mean, of course, you have to collect the data as well. So there's a 30% chance of rain tomorrow. So Bayes' law is very important law in discrete probability. Bayes' law is named for Thomas Bayes, an 18th century mathematician. So whatever you learn here, I mean, this probability is important in networks like traffic, route, and everything. Is I mean, this all created in the 18th century mathematician. This maths is not a new mathematics. Okay, this is all the classic mathematics that done by the mathematician or physicists last time. I think the most modern thing you learn is like Dijkstra algorithm, 1960. Most of it is like 200, 300, 200, 100 years old. In its most basic form, if we know P, if probability give event E given event F occur, we can apply Bayes' law to determine PFE as well. So this is the rule. This PFE is equal to PE given F times PF over PE. Okay. So you have a Bayes rules. This is the basic Bayes rule. PFE, PF over PE. So don't know. And then you have this additional Bayes. This is the additional rules of Bayes law. Bayes rule. PE is equal to P given F times PF plus PE given F bar times F bar. And then you have this one. So you have three Bayes rule. Number one, this is number one, the basic. This is number two, the general law of probability. And this is number three. Okay. So Bayes rules tells us how to invert conditional probability to find P B given A from P A given B. So common mistake is to confuse P A given B and P B given A. They can be very different. Okay. This is in the next example. So we have a toss a coin 5 times. Let H1 first toss. First toss is heads. So you have 1 over. This one you have 1 over 1 over 2. Okay, 1 over 2. So let HA all 5 doses ahead is 1 over 2 times 1 over 2 times 1 over 2 times 1 over 2 to 1 times 1 over 2 is equal to 1 over 32. Then pH1 HA is 1. pH1 given HA, the first one. If you want pH1 given HA all 5 doses is 1, but pHA is 1 over 16 probability of HA on the condition that H1 has occurred. So if you try to check pH1 over 2, pHA 132, so if you apply the Bayes theorem, the Bayes rules, you can get this one 1, pH1 given HA. This is all, pH1 is the first dose, it said given HA all 5 doses, so you have 1. But pHA1 is different. pHA1 is pHA is pHA given H1 is 1 over 16. Okay. So like this one you got P over 16 is like the first one you get 1 because pHA is 1 and others are 1 over 2, 1 over 2, 1 over 2, 1 over 2. So if you multiply is 1 over 16. So this is pHA given H1. pHA given the first dose is head. So the first event, the first times is 1 because H1 is first dose is head. And others are always 1 over 2. So you have 1 over 16. And if you try to apply these rules, you get 1. And same way, if you try to apply a formula, you got 1 over 16. Okay. Let's go to pHA given H1. So you have pH1 given HA okay, times P times pH2 over pH1. So you know pH1 over HA is 1 times pH2 is 1 over 32 and pH1 is 1 over pH1 is 1 over 2. So you have 1 over 16. So Bayes rules again. Now there is the probability that student pick a random studies math given that we know he studies physics. PAB, so you have now that probability that student pick a random studies math given that we know he studies physics. Math given that he knows studies physics. So you have a P, you have event A, PA is 55, PB is 25, PAB is 20. Okay, 20. So PA given B is this is a conditional probability. So you have a 0.8. Okay, PA into say B, PB or equal to 20 over 25. Okay, so here you get 0.8. And here's how to apply value to calculate the inverse probability. We know that PAB is 0.8, so you have here 0.36. PAB is study maths. This is study physics. Given he also study physics, you want to find the property of he studies maths. Given he will study physics. Okay. Given he study maths, property of study physics. Given he study maths as well. So you got 0.8 and you got 0.36. This is the Bayes rule. So Bayes rule also can be a total law of total probability if you have a set number. So you can also a summation of P You can also apply the sigma summation rules here if you have a number of sets. So if you have this one, consider measurement device that measures the packet header types of every packet that crosses a link. Suppose that during course of day, the device sample 1 million packets, of which 450% are UDP packets. So you have your P, UDP is 0.45, 500 TCP is 0.5, and the rest are from other transport protocol. P others 0.05. Given the large number of underlying observation to first, we can consider the probability that a randomly selected packet uses the UDP protocol to be okay. This one. Suppose that measurements show that 20% of the UDP packets have a packet size of 52 bytes. Okay, so you put P52 given as a UDP is 0.2. So if you want P, so this one if you compute the PUDP, have a PUDP and P52, PUDP and 52 is equal to P52 UDP times PUDP. This is conditional probability, so you got 0.09. What does 0.09 means? If you were to pick a packet at random from the sample, there is a 9% chance that it is a UDP packet of length 52 bytes. But it has 20% chance of being length of 52 bytes if we know already that it's a UDP packets. So 0.2 and 0.09. See the difference? This if we know that UDP packets, the probability of it, the probability that it size, the length of the packet is 52 is 0.2. But if you try to randomly pick up a packet, you know that it's is randomly the probability of its UDP and also 52 bytes in length is 0.09. So again, you can also use total law of probability, law of total probability, P52 and TCP is 0.9. For instance, if P52 given P52 and all the packets are known to be a length of other than 52 bytes, then you use the Bayes number 3, this one. Bayes law of total probability. PF plus PF and PE given F complement and PF complement. You just use that one. This is summation Bayes law of total. This law of total probability. This is a law of total probability. You have a summation. You have a number of sets. So you use this one. Okay, P50 UDP times P UDP, P50 TCP and P other. So you get 0.54. Okay. So you have a P52 UDP. You can also find P UDP 52, which is 0.167. So this is just like mathematics. That you know formalize the number. You have to know the formula, and you have to replace this and that. You have to know the okay. You just replace this. This is just a substitute types of mathematics. Okay. So select random box, the select random ball in box. So you have box 1 and box 2. Box 1 you have 2 green and 1, 2, 3, 4, 7 red. Box 2 you have 4 greens and 3 reds. If a red ball is selected, what is the probability that it was taken from box 1? So you define is select red ball, is select green ball, select box 1 and select box 2. So question what is PF given E? PF, okay, given is a red select red ball, but it's from the box 1. So you just use this Bayes theorem and you, okay, just try to PF is 1 over 2, 0.5. Probability to select box 1. PF complement is 0.5 as well. Okay, and then PEF is 7 over 9. We then select rainbow from 3 over 7. And then you just use the formula you have there, 0.644. This is if you select there. So what you have more boxes, you also can use the law of total probability. Okay, I think that's all for today. We're gonna go for spam filters and more on probability. So thank you very much and have a good day. For tutorial class, maybe we will so there should be no tutorial because tutorial is for tutorial. If you complete this, you're gonna have a tutorial. If you complete this, the discrete probability, you're gonna have tutorial number 1, or just give you assignment or something like that. Okay. Okay. Thank you very much.